Hello and welcome back to another episode of Math with Son. Today we're going to be doing some physics and we're going to figure out if an object has rotational equilibrium and sometimes how you can change the pivot point to create that rotational equilibrium. Okay, so this first example is wanting us to know if it has rotational equilibrium, if it has a pivot point at point A versus if it has a pivot point at point B, or maybe anywhere on this entire diagram. And if we want to do this, well, let's just start with pivot point A and see what happens. So we got one force going up and another force going up and then this third force going down. Now, if it is going up from pivot point A, it is 1 meter away, so we would do, and they're all perpendicular, so it'd be 1 times 12 in the positive direction because up goes counterclockwise and that makes it positive in this scenario. And then we would have 3 meters because 1 and 2 would make 3 in the negative direction, so this would be plus a negative 2 times 20. And then we would have to add 1 plus 2 plus 3 makes 6 times 8. And we can figure out what is the actual sum of all the forces. So we have 1 times 12, which that's 12, minus 40, plus 48. If we add all those together, 48 minus 40 and 12, you end up with 20 newtons in the positive direction, which indicates to you that this would be moving up. If the pivot point is A, it would be rotating counterclockwise in the positive direction for what we consider rotational symmetry and rotational forces with torque. Now, what if we change it to pivot point B? Because you may notice that 12 and 40 and 48 look like they could add to equal 0. If they add to equal 0, it's stable. If it's stable, it's not the moving. All right, so if we changed it to pivot point B, if we did that, what would happen then? Well, at pivot point B, you would have 0 meters away for that 20 Newton force, so that doesn't matter. But we'd be to the left of the pivot point by 2 meters, and because we're going to the left, that would actually make this 12 Newton force go clockwise, and if it's moving clockwise by essentially pushing it up, then it would be negative. Another way you could think of it is if it's to the left of the pivot point, it's going to be the opposite of the direction that it's facing, okay? So this is going to be negative 2 times 12, and then how does that compare to the positive 3 times 8? Well, that would be negative 24 and positive 24 newtons, and those would cancel each other out, giving you a 0 newton, and therefore, we'd be in rotational equilibrium, okay? So the main point of today's lesson is understanding that forces cancel each other out, and if they cancel each other out perfectly, it doesn't move, and therefore will not be rotating, okay? So, got a few more examples for you. This next one is going to be talking about a painter, and I like this one because most things in the real world would prefer not to be rotating. This painter is standing on a scaffold, all right? So this scaffold right here is being hung up, and the painter is standing 3 meters from the left. So he is over here, and he would really, really like to not fall off. And he would not be falling off if the tension on each of these is equal and it's in rotational equilibrium. Okay, so these tensions are fixed to where there is no rotational, no rotation happening. Now, the uniform scaffold weighs 100 newtons. That is going to be perfectly in the middle at the center of mass. We have 100 newtons, which is 2 meters to the left and 2 meters to the right. So if you think of it, the overall force would be 200 newtons regardless because it's going to be kind of in that center. All right, so it's 200 newtons facing down because 2 from the left or 2 from the right would be 2 times 100, giving you 200 newtons for the overall force. All right, with that in mind, this 800 newton painter is, let's do the left first. So if we wanted to do from this pivot point right here, this 200 newton force would be going down, so it'd be negative 200 newtons for that part, 2 times, because 2 meters this way, times the 100 makes 200, plus the painter who weighs 800 newtons, so this would be minus 3 times 800 newtons, gives us a total force of 2,600 newtons. However, in the negative direction, that is being counteracted by this force of tension, which is the main question here, is what is the force of tension on each end? Well, this force of tension is 4 meters away, because it says it's somewhere around here, 4 meters long. So all of this 2,600 is going to be counteracted by this 4 meters away tension. So if we have 4 times the force of tension, because it's 4 meters away, that would have to equal the 2,600. You may be asking, why didn't you make it negative? And that is because tension is going to be considered positive, plus you can think of it going in the upward clockwise direction. So if we divide 2,600 by 4, you get, drum roll please, 650 newtons. So this force of tension is 650 newtons. What would be the tension on the other end? Well, the other end may be a little bit less, because when you think of it from the other end, you got the painter who is closer to this pivot point. In fact, he's only he is only 1 meter away from that pivot point. And if he is weighing 800, that means that he is going to be applying 800 times 1, which is 800 newtons down. And then the center of mass being 2 meters away would still be 200 newtons down from the 200 times 2 times 100, making 200. All sorts of thumbs. Now, how much is that total? Well, that would be 800 newtons and 200 newtons. That would be 1,000 newtons total. He is being counteracted by this force of tension. So that force of tension would have to counteract that completely. So if we did 800 newtons plus 200 newtons plus the force of tension times 4, because it's still 4 meters away, a 4-meter platform, you would essentially be dividing that 1,000 newtons by 4 to get 250 newtons for the force of tension on this guy. The tension on the left side, okay? One more. This last one is going to involve angles, okay? So this last one's going to involve angles. It kind of is about equilibrium, but it's also just kind of a refresher about what happens when you have objects and forces on a wall and they're with angles. So there's 2 questions here. Find the tension on the actual cable, and then find the normal force on the wall. So the normal force on the wall will be this part, and the force of tension is only going to be the vertical portion of the tension of this cable, this 5-meter long cable. Okay? So the first thing we may want to consider doing is finding that angle so that we know how much is going to apply to the horizontal, and would also help to find this one over here, which I'm going to call theta prime. So in order to do that, we have opposite and hypotenuse. You could do sine -1 of 3 over 5 to get sine -1, 3 over 5. I'm pretty sure it is 36.8698. You don't need that many decimals, but sometimes it's nice because that's an intermediate answer. And it's also kind of not necessary, but I'll show you why in a bit. All right, with that in mind, we have this 300 newtons that is 4 meters away, and we have the cable counteracting that, keeping it stationary. So we would have 300 newtons times 4. If we add 4 times the sine of the angle we just found, 36.869, times the force of tension, that would have to equal 0, otherwise the shelf or whatever this thing is would fall over. All right, so 4 times the 300 makes 1,200 newtons of force there, and then we have Newton meters. Then we have 4 times sine of this stuff. What is sine of 36.869? If you do that, if you type sine of 36.89, calculator, sine of 36.869, you get 0.59999. Well, what is 3 divided by 5? 0.59999. So remember how I said you didn't really need that number? You could have thought of it as 3/5 this whole time. Times the force of tension would equal 0. We're going to do some manipulation. We're going to subtract the 1,200 over, which actually should be negative because it is going down. We end up with 4 times 3/5 times the force of tension equals 1,200 newtons. And we would divide by 4. 1200 divided by 4 is 300. And then divide by 3/5. If we divide by 3/5, we find out our force of tension on that would equal 300 divided by 0.6 is 500 newtons. All right, that's nice. You may also be asking yourself, well, it was 300 newtons down. Why is it only 500? Why do we have more in the force of tension on the cable? Because, well, flatly, part of that force is lost to this force of tension right here, and part of it's lost to friction and other aspects that may be happening. So now that we know that the full-on cable has a force of 500 newtons, how much of that is acting on the normal force on the wall? Well, the normal force on the wall is going to involve this angle up here, and that angle up there is complementary to this angle down here. So if this is 36.869, this would be whatever 90 minus 36.8698 is, which is 53.1. Okay, so if we're using that, we want to find the sine of that, which would be the horizontal force. So if we did sine of 53.1 times the 500, notice I'm not multiplying by 4 because it's on the wall, that's just the horizontal aspect. Sine of 53.1 is 0.8, which is 4 over 5. So if we did 0.8 times 500, you end up with 400 newtons for the force normal on the wall. All right, that's going to do it for this one. Until next time, everybody, stay positive, and I will see everybody later. Bye.